Hey, glad you came back. We're in section 7.2 on spans, and in this video we're going to do example 7.2.5, where we are asked to explore the geometric possibilities for the span of u, v, and w, where u, v, and w are three non-zero vectors in three-dimensional space. This example is broken up into three cases, so let's go ahead and start with case 1, where u is parallel to v and is parallel to w. So we know algebraic relationships between these vectors if they are parallel, and non-zero, we know that w must be a multiple, a scalar multiple of vector u. So let's call that multiple s. So w is s times u for some s in R. Similarly, if v is parallel to u, v must be a multiple t. Let's call it t of u for some t in R. Now we are asked to explore the span of these vectors, the span of u, v, and w, and that span is defined to be the set of all vectors y in three-dimensional space, such that y may be expressed as a linear combination of u, v, and w, so au plus bv plus cw for scalar coefficients a, b, and c in the real numbers. Now, we can figure out what's going on perhaps by the picture, but we want to look at this algebraically and prove that our intuition is true. So we are going to take these algebraic relationships that are based on the parallel relationship between these vectors, and we're going to substitute these in to our linear combination, which means that we can say our span is the set of all vectors y in three-dimensional space, such that y can be written as a times u plus b times v, but v is t times u, so b times tu, plus c times w, but w is s times vector u, so c times s u. This time now we have a, b, c, s, and t in R. That's a lot of scalars, so let's see if we can reduce that a little bit. Y is, in the real numbers, the span of UVW is therefore all y that can be written as, and we can factor out all of these constants. So a plus b times t plus c times s times vector u. Again, we have a, b, c, c, s, and t in the real numbers. Now, if we have a plus b times t plus c times s, if these are all numbers, right, if these are all just real numbers, combining them this way just makes another real number. So since a, b, c, s, and t are arbitrary, we can just call this some arbitrary number k. So the span of u, v, and w is all vectors y, such that y can be written as k times vector u for some k in the real numbers. Well, we know what that is. We explored that in the previous video. That is exactly the definition of the span of vector u. And the span of vector u when u is non-zero is a line through the origin in three-dimensional space. And so we can imagine that this span, just as in the previous video, right, if we take linear combinations of these vectors, we're going to end up by getting vectors which are really just multiples of u. So in the first case, that the three vectors are all parallel, the span of u, v, and w yields a line through the origin. Case 2 says, well, what if now we know that u, v, and w are coplanar, but not all parallel? So the diagrams here have shown you two cases. So in this first case, w and u are parallel, but v is not. And in this second diagram, we have three vectors which are all coplanar, but not any pair of them is parallel. So in each of these situations, we're imagining that these vectors can be contained in a plane. And so this group of vectors, these three vectors, can be contained in a plane. And so what you are going to do in the exercises that accompany these videos, in the exercises, you will make a similar argument. You will make a similar argument to what we did just above in A, and you will show that the span of u, v, and w in these cases is the same as the span of u and v, where u and v are always taken as non-parallel but coplanar vectors. In other words, the span, as we saw in the previous video, the span of two non-parallel, non-zero vectors is a plane through the origin in R3. So we have one case where the span of u, v, and w gave us a line. We have another case where the span of u, v, and w can give us a plane. There's one more case that we're going to look at, and that is case 3. What happens when our three vectors u, v, and w are non-coplanar? And so what we're talking about here, in case it's not entirely obvious from the diagram, is that we have vectors maybe u and v, which are in the plane that I've drawn here, and then we've got a vector w, which is not in that plane. So that vector w is coming out of the plane, has some sort of height above the plane there. So similarly, I'm going to leave this as an exercise, right, that you will do in the exercises. This one is a little more involved. In the exercises, you will prove that the span of these vectors, the span of three non-coplanar vectors, is all of R3. But what I will do is give you a little bit of an intuition as to why that is reasonable. Right? So this is defined as, right, the span of vectors u, v, and w is all vectors y in three-dimensional space, such that y can be written as a linear combination. A u plus b v plus cw for scalars a, b, c in R. So let's just take a second to imagine, what if we were talking about the case, for example, where A and B and C were just one? What would we get if we applied our geometric addition rules to just u plus v plus w? Well, we can sit here and think, well, let's do this two at a time. If we do u plus v, well, u plus v, we can apply the parallelogram rule. If there's just two vectors, we can imagine applying the parallelogram rule and getting a vector u plus v like this. And then from that resultant vector u plus v plus w, well, that's adding another parallelogram rule to that result. So parallelogram rule between u plus v and w. So the result of our vector here, this is actually, I mean, it's something like, you might call this a parallelepiped rule, but that's neither here nor there. U plus v plus w would be the resultant vector there. So you can see that that vector, when in the very special specific case where the coefficients are all 1, that vector is being pulled into the sort of the center of the parallelepiped, if you will, between u, v, and w. Well, now imagine, and I'm giving you just a little bit of a geometric intuition, imagine that we could scale u, v, and w with scalars. That's why they're called scalars, right? We could change their length and we can change their direction. So we might be able to pull vector u down this direction, right? And now if we added between u, v, and w, we might get a vector off in this direction as the result of u plus v plus w. And if we could then maybe change vector v and make it long and in the other direction, right? If we could bring vector v down here, and then we add it together, v and u and w, we might get a resultant vector sort of off in this direction. And so this ability to take all scalar multiples, right? You can change the length, you can change the direction, and add them all up. You should hopefully get the impression that you can get a vector anywhere in three-dimensional space. And since you are taking the span, that means you're taking all possible linear combinations of these, you are getting all of R3. Now, that is just a geometric intuition as to why this is true. In the exercises, you will actually give a formal argument as to why the span of three non-coplanar vectors in R3 is all of R3. So let's just read the last remark on this page, and that will be the end of the video. So what we should sort of take stock of here is in this example and the one in the previous video, we saw that to generate a line through the origin, one vector is sufficient. But we just looked at this example and we can generate a line with more vectors. We did it with 3 if they are all parallel. We also saw that a plane, pi, can be generated with 2 vectors. But we just looked here and we said, well, it can be generated with more too if they are all coplanar. These are specific instances of relationships called linear dependence and, well, in the case of the non-coplanar, independence. And we're going to look at that in the next, not in the next video, but in the next section, in section 7.3. So we're going to generalize these types of relationships to larger collections, right, of vectors in higher dimensions, in dimensions that are not just the three-dimensional world or three-dimensional space that we live in.